This is section 5.2, the natural logarithmic function integration. Last section we did derivatives. All right, so we know that from our prior work that the derivative of the natural logarithm of the absolute value of x is 1 over x. And we also know from even earlier than that, as a consequence of that, that if we have some inside function represented by u, that we're taking the natural logarithm of the absolute value of u, that's going to be 1 over the something, 1 over u, times the derivative of that something, times du dx. Okay. So, just like all of the other antiderivative rules that we encountered earlier, that once we know the derivative rule, we can then imply an antidifferentiation rule for that. And so what that means is, for us, that the integral of just plain 1 over x dx should take us back to what it started as, so that this is the derivative answer for something. And what that is the natural logarithm of the absolute value of x. That absolute value is, no pun intended, no, actually I always intend them, absolutely necessary that you put the absolute value around that x, because otherwise we'll have a restricted domain, much more restricted than we want it to be. And by the same token, if we have 1 over u, where u is some function of x, multiplied by du, its derivative, then the antiderivative of that, by the same token, will be natural logarithm of the absolute value of that thing, u, plus c, of course. All right. So, for example, if we had 2 over x dx, that constant 2 can come out in front, leaving 1 over x dx. And using the rule above, that's going to be 2 times the ln of the absolute value of x. Please don't forget the absolute value here. Plus c. Please don't forget the c. So there's all this stuff that you want to make sure you do correctly. Now, because of some properties, we could, if we wanted to, take that 2 back in, that coefficient, back in as a power on the base absolute value of x. And the absolute value there is redundant. Let me put parentheses around this. The absolute value is redundant because if you square x, the answer will be non-negative anyway. And so I can simply write natural logarithm of x squared. So if you know that that argument is definitely already not negative, then you do not need the absolute value and you can get rid of it. You do that at your risk, however. Don't just willy-nilly drop it, because that's not going to happen all that often, and some of you will accidentally do it when you're not supposed to, and that's a pretty critical error. So only if you're absolutely certain that that argument of the logarithm is non-negative, then the absolute value is superfluous and you can remove it. Now, integrals that use the log rule that we just talked about are going to be sort of disguised. For example, if you have a rational function where the numerator is a degree greater than or equal to that of the denominator, division may reveal a form to which you can apply the log rule. We'll see that in example 5. All right, so let's do example 5. X squared plus x plus 1 divided by x squared plus 1. All right, the rule for rational functions and integrals of rational functions is this. Make sure you take note of this. If the degree of the denominator, let me start over. if the degree of the numerator is greater than or equal to the degree of the denominator, divide. Use long division. So the numerator degree here is 2, and the denominator degree is also 2, so it's equal. So that means that we will divide first. So we're going to do polynomial long division. Remember, in polynomial long division, you insert zeros for any missing terms that exist. We're dividing the denominator into the numerator. And what I'm going to ask myself is, what would I multiply the first thing outside x squared by to get the first thing inside x squared? The answer to that is 1. So if I multiply 1 by x squared, I get x squared, plus 1 times 0x is 0x, plus 1 times 1 is 1. And then subtract. Please keep in mind that you're subtracting all the way across. X squared minus x squared is 0x squared. I'm not going to write that down. X minus positive 0, oh, there's no positive 0. But anyway, x minus 0x is x, and 1 minus positive 1 is 0. So my remainder is x. And so what that implies is that that fraction in the original integral, after dividing, is the quotient, the thing on top of the division symbol, 1 in this case, plus the remainder over the divisor. And of course, the quotient is going to be some polynomial. This happens to be a polynomial of degree 0, which we know how to do. That's easy. The integral of 1 is x. Easy peasy. So I'm going to just separate these in my head and write down the answer to the first part, and then delve into the second part a little bit more deeply. So here's where there's a hidden 1 over u. And you have to be on the lookout for this. It's going to start being more and more obvious as you practice this. So if the whole denominator is my u, check out and see what du is. And if that is the numerator or easily obtainable by introducing a new constant to be the same as the numerator, we're in business. So I need x and dx, both of which are necessary, and I have both up here in the integral. So the only thing I'm missing is the 2. So if you'll remember, what we do there is we multiply inside by 2 so that this x and this dx and this 2 become du. And when I multiply inside by 2, I have to, at the exact same time, multiply outside by its reciprocal, 1/2. Notice I didn't put a constant of integration in yet because I haven't gotten rid of all of the integrals. So I'm not worried about that c until all the integrals are gone. All right, so this becomes 1/2, and the x, dx, and 2 become du, and that leaves a 1 in the numerator over our u. And so we know that that is natural logarithm of the absolute value of u. And now that the integrals are gone, now it's time to put in the c. I talked about earlier, you don't want the tardy c, the c that comes late to the game. It's got to be put in right there in the problem, as we did. Okay, so now rewriting this in terms of x completely, we'll replace the u with x squared plus 1 plus c. Now I'm going to allow you to leave it like this if you want to. So I'm going to make this a parenthetical further simplification that you don't have to necessarily do because I don't want you to have to worry too much about it. If you want to leave it in that last step where you have the absolute value there, even if it's redundant, it doesn't hurt anything for it to be there. But in this case, x squared will always be an answer that's 0 or bigger. If you add 1 to that, that answer will always be 1 or bigger, so it's definitely not negative. So it is possible in this case to take away the absolute value. You are still going to have to write parentheses here, so I don't know that it saved a whole lot. You had to write an extra line, but it is a good simplification. It's definitely valid. So good to know, I suppose. that you may see some answers, especially in the answers in the book, where they get rid of the absolute value when they can. Just alerting you to that fact that they will do that. On the next page, there are some guidelines for integration. You should probably start to internalize that pretty fast. The first thing to do is to know your integration formulas. Then, if you can find an integration formula that resembles all or part of the integrand, and by trial and error you find a choice of u that makes the integrand conform to the formula, you're good to go. Keep on trucking. If you can't find a u substitution that works, try altering the integrand. There may be a trigonometric identity replacement, a multiplication by 1 in the form of something over itself, addition of 0 in the form of something minus itself, or long division as we just did, or something else perhaps. So be creative. I'm going to skip 4. And then you can, if you want to, I'm never going to require that you do this, but you can always check your result by taking the derivative of your answer, and you should get back to the original integrand, the original problem's function behind the integral sign. All right, so now let's do another example. We have here a differential equation. Remember, a differential equation is just an equation that has a derivative of x, a derivative of y in it. So it has a dy dx in it, I suppose you could say. So if I anti-differentiate both sides with respect to x, which is something we can do, just like you can take the derivative of both sides with respect to x, you can anti-differentiate on both sides with respect to x. And the antiderivative of the derivative of y is y. That's why we did it. Now notice I'm not putting the plus c there. Technically it has a plus c, and the other side will have a plus c sub 2. It's a different c. And if you subtract c from both sides, a constant c2 minus another constant c would just be another constant. So instead of having to go through all of that, we're going to let y stand by itself here, and when we finish the problem, we'll put the plus c in on the right side. So the big question here is, well, what are we going to do in this problem? There are several different things we could try. It could be, for example, that u is just the x part of that denominator, or it could be that u is just the ln of x, or it could be that u is the whole denominator. And until we play with that, we really don't know. So let's see what du dx is. Oops. Du is in each case the derivative of x is 1 dx in the first case. In the second case, du is 1 over x dx. In the third case, oh my gosh, that's going to be a product. So that's going to be first times the derivative of the second plus the second times the derivative of the first, which is times dx, which is 1 plus ln of x dx. So of all of those, you want to find the one that, if we say, for example, let u equal x, the only other x thing we can have in that problem at that point is dx according to its derivative, and that means we haven't accounted for the ln of x. So this one's no good. Let's go to the last one because it's pretty nasty. If we're using that denominator, x ln of x is u, that means we have to have a 1 plus ln of x in the numerator, which we don't have. We can introduce constants by multiplying by a form of 1, like times 2 inside times 1/2 outside, as we've seen before. But we can't introduce that 1 plus ln of x. So that's also a bust. So I hope that the middle one is actually going to work. If u is ln of x, that means that we have to have, besides that u, we have to have an x in the denominator and a dx. Well, that, thank goodness, is exactly what we have here and here. That's this. So the circled stuff is my du. So that means that this will become the integral of 1 over, and look at the definition of u that made this work. That was ln of x, so the ln of x becomes u, and the circled in green things become du. So the antiderivative of 1 over u du is the natural logarithm of the absolute value of u, please don't forget that, plus c. Then, going back to the original variable, this will be y equals the natural logarithm of the absolute value of ln of x plus c. Now, are those, is that absolute value necessary? Actually, it is, because remember, the ln of a number between 0 and 1 is negative, and so natural log of x can have negative results, and we can't take the outer natural logarithm of that negative inside result. So we can't get rid of the absolute value. We have to leave it in there so that we're always getting answers for all positive numbers x. And that's our final answer. And you've probably never seen something that looks like that. The natural logarithm of the absolute value of the natural logarithm of x plus c is probably not a function you've dealt with like 6,000 times in your life. So you're going to get some interesting things. Okay, example 8. The integral of tangent of x dx. Let's see, this one, it's kind of hidden. I think I kind of mentioned that before, that sometimes it is going to be sort of hidden from you. But if you think about tangent of x, think about an identity for tangent of x. Isn't that the same thing as sine of x over cosine of x? So if we do that substitution, we now have a denominator whose derivative is in the numerator, or sort of in the numerator. If u is the denominator, cosine x, du is the opposite of sine of x multiplied by dx. So what we have there is everything but the negative sign. I have the sine of x. I have the dx. All I need is the negative 1. So I'm going to multiply inside by negative 1 and outside by negative 1. Negative 1 times negative 1 is, of course, just 1. So I haven't changed the value of that integral. And this will become the opposite of, and then the negative 1 times sine of x times dx is my du. So all of that becomes the du. And what I'm left with, other than the things I underlined, is 1 over cosine x, which is 1 over u. So this gives us the opposite of the natural logarithm of the absolute value of u plus c. And then going back to the original variable of the problem is x, so we're going to replace u with cosine x. Cosine of x does sometimes take on negative values, so I cannot get rid of the absolute value this time. It's absolutely necessary to keep. Okay. And there's an answer for that one. So if you'll look at the next page, the last page of the notes, the integrals of the 6 basic trig functions are summarized below. I'll write them in case you don't have that right in front of you. These are all things that you need to add to your list of integrals to know, some of which we've already talked about. It's just a summary. The integral, write that better. The integral of sine of u. So this is a little bit stronger form because u can be any function of x. as long as we have the du behind it, using u substitution rules, is negative cosine of u plus c. The antiderivative of cosine of u du is sine of u plus c. The antiderivative of tangent of u du, the one we just derived, is negative natural logarithm of the absolute value cosine of u plus c. And we could have done cotangent in a very similar fashion. Rewrite it as cosine of u over sine of u and derive this one. So I'm going to leave that to you as an exercise. If you want to figure out if you can derive that one by yourself, you should end up with natural logarithm of the absolute value of sine of u plus c. And these I give you without proof. I'm just going to tell you what they are. You need to commit these to memory. The integral of secant of u du is the natural logarithm of the absolute value of the secant of u plus the tangent of u plus c, and the antiderivative of cosecant of u du is equal to negative natural logarithm of the absolute value of cosecant of u plus cotangent of u plus c. Okay, so that ends the notes for today, and I will see you next time.